an excellent talk, for an excellent overview. And
Against your permission, because the interviews
oh,
are
interviews are going on. I request Professor Sir to please honor the memento for a wonderful talk, for a wonderful overview. So we are planning tomorrow a visit to all the centers
Yes,
and all
yes.
the instrumentation
And
facilities.
moreover, I am happy to inform you that we don't have any technician. Whatever the research facilities are with us, all are run
We are
by
running.
our students, PhD students.
Yes, sir.
That's the best part of
Thank you so much, sir.
processes which I am talking about, magma melting. And during the magma melting, what happens? Only those elements which are compatible to the minerals which are crystallizing out of one series, if they are compatible, they will go into those minerals. If they don't go into those minerals, they are incompatible. So we divide compatible and incompatible elements, and accordingly, initially only smaller metal ions, for example, Fe and Mg, goes into pyroxene and olivine minerals. So the basaltic magma get concentrated in, and the liquid magma will have larger ions, remaining larger ion. So So when magma evolves, initial minerals take up only compatible elements, which can go to the structure of those minerals, pyroxene, olivine, or major primary minerals, and remaining will go to liquid. So accordingly, we have compatible and incompatible. The larger ions, for example, large ion lithophile, potassium, barium, sodium, calcium, they will remain in the magma. So when the remaining magma will go up because of buoyancy, we'll have these things. But at that time, silica rich minerals will form. In those minerals, potassium and barium and rubidium will go. So ultimately, large ion lithophile go into the granite composition. So continents are rich in large ion lithophiles, thicker cations. Basaltic magma, basalt, therefore oceanic crust is rich in, because of this process, compatibility and incompatibility of elements and magma evolution. And we have rare earth elements, you know. So we have major elements, we have trace elements, major elements, 10 elements, which make major primary mineral. There are 99% of this periodic table are major, 99% of the earth material is made by major elements. Aluminum, silicon, calcium, sodium, potassium, titanium, phosphorus, and plutonium. And rest of the elements are trace elements, less than 1%. Among trace elements, there are REs, rare earth elements. And rare earth elements are, as well as scantium, yttrium, they are nearby. They are very important uh, pathfinder for the magma evolution and rock formation. These lanthanides are basically coherent in nature. They behave similarly. Even then, because of the lanthanide contraction, we have light rare earth and heavy rare earth. This light rare earth and heavy rare earth elements we have differently. Although they are coherent, magma has these trace elements, but these two groups, and as well as europium, because of europium have two oxidation states, europium 2 plus and europium 3 plus, they behave differently. And accordingly, we have upper continental crust. The lighter rare earth are compatible. Lighter is incompatible. The heavier rare earth are. So what happens when magma comes up? Those magma leave the light rare to the wave, whereas takes up the heavy rare. As magma goes up, you see the upper country crust is enriched because the remaining magma came later, bringing lighter rare. They are enriched. Whereas the basaltic material, mid-oceanic basalt, is nearly flat. The older rocks, which were less evolved, have nearly flat. Okay, and therefore we have upper continental crust, and this is the fractional crystallization of magma. See, initial 0.25 melting, percent melting. It is done in the lab experiment. As you melt the rock, more and more light rare enriches. In the and see, accordingly, with the evolution of magma and crust, we have this is present day upper continental crustal composition. If you have older continental crust, for example, more than 2.5 billion years ago, they will have a flat crater pattern because those are less evolved. They were initially taken up by the mantle, and because of this process, mantle also evolved. Many times it is happening since its origin of the earth. Magmas are coming, taking away the compatible elements, remaining melt will have incompatible elements. So the magma, the mantle is also evolving. The magma which was taken from mantle 2.5 gigaannum ago was different than today. So by dating also we can find out what was the nature of magma, then nature of rock. How we find out nature of that magma of that time? These older continents have the remnant of those continents. If you put Harvard Cretan, the rocks are of 2.5 gigaannum old. So those chemical signatures, if you analyze them for rare earth elements or isotopes and date them, they tell about the mantle and crust of that time. So accordingly, we have upper crust, middle crust, and lower crust compositions. This bulk crust, they are more. The upper crust is more evolved. As you go up, more and more light. LREs are increased, and accordingly, we have. See, there is one question many people ask: why we? And these are normalized by chondrite or the original composition of the mantle. We normalize because otherwise they will have this kind of pattern. And after we normalize, there is a smooth pattern of REs. So this was the primary process by which different rocks are formed, and these rocks have different compositions, different REs patterns. But you might have heard about rock cycling. When the magma reaches to the crust, it doesn't remain igneous always. It has to weather. It has to produce aerosols. If it doesn't weather, because of the effect of temperature, pressure, time,
You only can say it.
Because he has to. नहीं अभी तो 25
So, weathering is controlled by rock characteristics. I have explained different rocks have different compositions and different structure also because of structural processes going on, tectonic processes. They are crushing the rock. Sometimes they are less crushed. For example, if you take the granites of Bundelkhand Mekong will have different composition than the basalt of Deccan tracts. It is depending on the evolution of magma. When that magma came up, where they have, how much it got evolved, at what stage it was quenched for crystallization. So these all control the rock characteristics. Basaltic rocks, the rocks which are, I'm not going to explain much about weathering, but the rocks or minerals which formed at high temperature will weather faster, you all know, than the rocks or minerals which formed at later stage. So granites is less weatherable, basalt is more weatherable. Basaltic minerals, for example, olivine, pyroxene, more weatherable. Granitic minerals and quartz is least weatherable. So rock characteristics can slow the geomorphology of that area, then slow how much water can be hold by that geomorphology. More water, more time, more weathering. If the slope is high, all water get run off, no water, dry setup. So all these affect the weathering process. A longer time, longer exposure, more. So I have explained about the composition and also the climate which affects accordingly. For example, more water, higher temperature, we have more chemical weathering, low temperature, low water condition, less humidity will have more. For example, in hot as well as cold conditions, aridity affect the weathering. More physical weathering will be there, whereas where more water is available, more chemical weathering will be there. Mechanical and chemical weathering.
ज्यादा क्लिक करते हैं कि तो नहीं बोल रहे पता नहीं सेल डाउन तो नहीं हो गया आराम से हाँ चलो हो गया एक बार क्लिक करो ऊपर प्रेस करते हुए बस छोटो से प्रेस में हो गया ना अभी दोबारा करते एक बार हो गया थोड़ा डिलीट सेल पड़ेगा यहाँ से यहाँ
बस और एक पीछे नहीं हो एक और एक बस ये so basically
सर से पूछिए इसको
physical weathering
बैठ
in the natural processing
मेरे को समझ नहीं
size
आया
evolution process is an important process.
शिवाजी हमारे चेंज हो रहा है उन्हें चेंज करना
ये आप चेंज करते रहना
सर उन्हीं की प्रेजेंटेशन
So during the size evolution process,
ये मैं सिस्टम 5 मिनट देना इसको दोबारा इसमें लगा देने सब कुछ चेंज करते हैं लैपटॉप हटा देते हैं
चाय के टाइम
and this
सारे
surface
टाइम
बस अभी चाय 5
teaching
10
process not
बस
only
इनके
with
बाद
the,
से आएगी ना बस ठीक
the
तब
quantum
दूसरा
process,
कर
also the aerosol chemistry, how
वो
much
तो
it
नहीं
can
पिटी
hold
है ना इसके अंदर
more the surface area that affects the holding aspect of that thing, whether it's aerosol or dust. And accordingly, next Next. So these are the main physical weathering processes. I am not going to be in this. Next, we all know products of weathering. We have solute phase. After weathering of minerals, we have solute phase. Next, a mineral whether to, if you take basalt, it will weather to form clay minerals. Soluble phase is sodium and potassium, calcium, and silica. If we have rich minerals, we have goethite, for example. And if we granite, if we weather granite, it will also have clay minerals, but solute phase will have sodium and potassium and silica. These will go to. So, but see, basalt and granite, two different rocks will give two different kinds of clay minerals. Next. Next. These are the chemical equation by which we have. Next. So two different kinds of clay minerals are formed, and these clay minerals are formed of next silicon and aluminum, silicon tetrahedron C and aluminum octahedron C. Next, these sheets are one above another in some ratio. For example, 1:1 ratio silicon tetrahedron, that gives carolinite. 1:2, that gives smectite and illite. Next, so 1:1 clay mineral, only one tetrahedral sheet, one octahedron. See, aluminum and tetrahedron and silicon tetrahedron, aluminum octahedron. These don't have any other cations. Next, 2:1.
ऐसे करके देखो
We have one octahedral sheet of alumina, and then two tetra, and these have something.
तब वो मैं करता हूँ
Sometimes
उसके बाद
silicon
नहीं
tetra, silicon is replaced by aluminum. There is a charge difference, and also, and because of that, there are negative charges on these clay minerals. And this is one important process by which aerosol or suspended load chemistry of river is governed. And we see, you see the how much suspended, the distribution of the suspended load material worldwide. And these materials become part of the aerosol. These loose materials, which have clay minerals, which have physically weathered primary grain, mineral grains, or metamorphosed grains. All of these control the distribution of, and basically the river processes produce and deposit initially these loose materials in the floodplains. You see the distribution of floodplains and also the desert. Nice. Next. So I have given some idea about weathering, but how do we quantify weathering which is useful for aerosol study? Among all the elements, next, which are there in the minerals, there are alkali and alkaline metals, and some of them are, during weathering, what happens? They are released by the mineral. Whereas some of the elements are immobile, they don't go. They remain as clay or iron oxide or aluminum oxide as solid phase. So solute, alkali and alkalines go away as solution, whereas aluminum, gallium, titanium, REs, they remain as their oxides or hydroxide in the weathered material. What happens? And silicon is generally retained as quartz or becomes silica if it get dissolved. Next, you see, on the basis of the enrichment of these metals in C, as well as the residence time we plot here, you can find out which are mobile and immobile. You see, These are more highly mobile elements. Sodium, magnesium, boron, potassium, strontium. Potassium is mobile, but what happens? It gets attached because of its large iron size. It gets attached to the clay minerals, negatively charged clay minerals. It remains in the soil. Or aerosols, for example. Aerosols, I basically, is my thinking that they are floating soil in air. Aerosols are floating soils. They have similar because they get originated. All the organic matter and other things are becoming soils. Therefore, they're floating soils. So, whereas you see iron, ammonium are less mobile elements. What we have done, Nesmith and Young has done. Next. They have devised a formula for chemical index of alteration, and that is ammonium over aluminum and all other mobile elements. It is the ratio of mobile and immobile membrane, immobile and mobile elements. So, and because this earth crust is mostly composed of feldspar, 50% feldspars are there. It gives better idea about weathering on continental. Okay. So this CIA value is effectively measures the degree of alteration of feldspar to clay minerals during weathering. Next, we can calculate chemical index of alteration of, for example, Claudians have come for aerosols. So I will say aerosol weathering index can be particulate matter weathering index can be calculated. How much weathered material it has. If it has more clays, therefore more aluminum. And the nature of aluminum, for example, you see in this triangular diagram, the same CIA ingredients are there. Aluminum, sodium, calcium, and potassium. Okay, and these are molar bases. You see, kaolinite, gibbsite. They are. This kaolinite is 1:1 clay mineral. One octahedral layer, one tetrahedral layer. Octahedral is aluminum, so 100% aluminum. Silica is not in the formula. So it is 100% aluminum plots and the Al protein. Whereas, see natural water. You see, if you plot natural waters here, it will not have aluminum, iron, only in this formula calcium, sodium, potassium. Potassium is also not there because that is held up with the soil. Negatively charged clay particle. So you have natural waters. See, most of the unweathered rock being typical igneous composition plot here. You start weathering these rocks. You go, this blue line is a weathering trend. That will go along the weathering trend. And what happens? Initially, illite will form. Or ismetite this side. Because ismetite doesn't have potassium. So they plot this side. So initial weathering, intermediate weathering, products will have ismetite and illite, and shale is a rock which has mostly clays. So see, shales are plotting in between. If you take lowest composition is somewhat, it is very mixed material. Loess are very mixed, wind blown material. Okay? That will have less clay, more silty kind of material, more unweathered material. They plot near to the igneous composition below shale. Lowest less weathered, more weathered shales, and highly weathered material will plot towards shale. You can use ACNK diagrams of CIA chemical index of alteration to understand what is the source of these aerosols. whether a terrain which has weathered material or a terrain which have less weathered material. If aerosols take up material from a place, for example, if you go to Leh Ladakh, more and more unweathered material is there. If you take silicate phase material, silicate materials that will have low indexes. If you go to Thar desert, somewhere higher chemical index of fertilization. If you go to basaltic terrain, like if you take up aerosols there, that will have less weathering, even as less than 50, because those will have the minerals will be more mafic minerals. So those will have very less CIE index. So you can use these major elements itself as indicator of provenance. We say provenance, source area for the sediment. This can be used for aerosols also. Next. So we were talking about shale, loess, eroded material. You see, the post-Archean, all the shales of the world have been sampled, analyzed, and average compositions of these are brought in post-Archean. Early Archean shales have different composition. As I said, they were originated from less evolved crust. So they have somewhat lower LREs. Okay? But post-Archean shales and all the sediments which originate from this continental crust will have this type of pattern. Okay, next. See, we have plotted cells and layers here. Okay, and these authors have calculated, modeled the crustal composition. How much similar they are? Why cells and loess's are very much similar? Why they have? We have also worked on loess's and aerosols of the leaf. This will tell. Delhi loess's. We don't say loess's, we say loessic sediments. They plot within this range only. I'm not bringing that figure here, but they also plot in this range. Why they plot? When we sampled from Delhi from different places, they all bang on at one position. Then we thought, where from it is coming? Why? How they are so much homogenized? Okay, because Yamuna river plain is very nearby. Also we did some isotope work, and then we found out that they are originating from Thar desert. The dust is blown from Thar. They are so homogenized. By the time they reach to Delhi, they have this kind of. So aerosols can also be identified how much they have traveled. More and more travel, more similarity with loessy patterns. Shale also. Shale is the material, fine material which is supplied by the rivers to the ocean, and these fine particles get deposited at the deeper part of the ocean. Similar way, one is in aquatic system, other is in air. But similar way, they get homogenized. All the cells have
ये वाला पेन
in the previous slide similar RE pattern.
मैच करेगा
So RE patterns can also be used to understand lower aerosols, and many people have been very effective. Next slide. See, we had glaciations. During the glaciations we have peak aerosol activities. If you find out these loessic deposits have formed during the Pleistocene glaciation period or anywhere in the world. And that is again controlled by climatic setup at that time. And this climatic setup by climate is controlled by igneous processes. Ultimately, you see the CO2 sink and CO2 source all through physiological processes. See, CO2, there is solar radiation as well as CO2 from volcanic activities by the tectonic processes. These two control the climate, and climate went on cooling and drying. Okay, cooling and warming. Cool is dry situation. In dry situation, aerosol activity increases. In cold areas, there is more. There can be more aerosol. There is no humidity, so the particulates can this loss very easily. There is nothing to hold. There is no water. So these processes are this tectonic processes, aerosol activities, climate, all are one way connected. Next. So here I have put climate, weathering, and then erosion. Orogeny and atmospheric circulation, all these, this corner. I want to bring it weathering, and for weathering there is a source material, how geology is controlling the chemistry. Next. Now, I'm coming to the state of the art. इसके बाद में चाय पीने के बाद नहीं ऐसा नहीं होगा
सर एक क्वेश्चन पूछ लूं
हाँ
छोटा सा सर राजस्थान का जो आली पैटर्न है और जो दिल्ली में लो इसका पैटर्न है वो क्या अलग है सर
नहीं सेम होगा ना
नहीं आप कह रहे हैं वेदरिंग से
वेदरिंग से तो उसमें वहाँ
जो अनवेदर्ड है सिमिलर है ठीक है
सिमिलर हो लेकिन जो इसमें दो चीजें हैं there are two things you have to see the pattern and abundance. Abundance is lower there because more quartz grains are there on the top. So their abundance are lower. But upper see, you see the upper continental crust composition very much similar. These all patterns are very much similar, but basalts are different. Other rocks are different.
यूरोपियन एनोमली भी वैसे है
Same. So I discussed about the melt extracted from the mantle and goes up to make the continental crust. I discussed about the continent incompatible and compatible elements. Okay, so mantle becomes incompatible element depleted. Okay, continental crust becomes incompatible element enriched with the time. See, crust brings because mantle magma when comes up. It is the remnant liquid coming up. Liquid will have incompatible elements. All the compatible elements has gone to the minerals which deposited there itself. Lower crust. But the upper crust will have more incompatible elements. Incompatible elements will bring the large ions like rubidium. Okay? The melt extraction will bring more rubidium, more rubidium, more lanthanum. Next. And these rubidium decays by beta to the strontium 87. Rubidium 87. Strontium 87. So when rubidium is taken up by the crust, this rubidium goes up disintegration and there will be strontium. With time, more and more strontium will be 87, not 86. Strontium 87 will be there in the continental. Similarly, samarium neodymium system, we have samarium disintegrate to the neodymium 1. What is it? Samarium, among samarium and neodymium, samarium is held up. उसका उल्टा है यहाँ पे. samarium is held up in the mantle, and with the time it converts to the neodymium 143. Next. So this is about what happens. The rocks which has formed with time, this also, mantle composition also evolves. Neodymium composition evolves. The isotopic ratios evolve. For example, when melt is extracted from the mantle, it will have same 87 and 86 strontium ratio as well as 143, 144 neodymium ratio. But for example, mantle which is holding samarium is producing neodymium 143. So with time there will be more enrichment of 143 in the mantle. Whereas for strontium, same melt came, but with the time continental crust will have more and more strontium 87 because Rb which has come up is getting dissociated. Okay? So this systematic is used for next. So we use strontium 86, 87, 86 as values directly, but for neodymium 143, 144 ratio to make more visible, we use this formula. We calculate epsilon neodymium value. You see, if a magma is at 3 gigaNm, if a magma is extracted, mantle will have more and more positive side evolution for the value. Whereas for crust it will go more negative side, towards more negative side. Okay? Next. Systematics have been used for undefined sources for endogenic plane and third desert. Okay? Next. Whole endogenic plane is made up of sediments brought from Himalayas or from southern Africa. Okay? Whether those sediments are brought from Indus, Vyas, close to Brahmaputra, Ganga, Yamuna, Brahmaputra. They are bringing Himalayan sediments. Himalayan sediments are supposed to be very high strontium 87 values. Very high. And it is also found out that during glaciations, the weathering was very effective and lots of strontium 87 was supplied to the river. Even when we take coarse calcium carbonate enriched foraminifers, fossils enriched cores, when we analyze them, these foraminifers, we find that during glaciations lots of strontium, because strontium replaces calcium in the mineral. So that indicates about the weathering of calcium bearing mineral. More and more Himalaya is very much enriched, highly enriched in strontium 87 because of metamorphic processes in Himalaya. Lots of tectonic processes, metasomatism processes that has brought rubidium to the granites of the Himalaya, and that rubidium with time converted to strontium 87. Therefore, high strontium 87 delivery happened during Pleistocene glaciers. And we find that in the last 45 million years, strontium 87 increased because of very high weathering and delivery by Ganga. The solute phases containing strontium 87, strontium, calcium, other soluble ions. So it is not only for the water, for sediment also. Those sediments which are supplied from the Himalaya very high at 87, 86 ratio. Whereas next, Next. So it is not only the geochemical composition of both subcontinent, it is also the climate. Rise of Tibet has controlled the climate so that we have moisture there, we have rivers there, and therefore whole sedimentary process there, cycling and recycling of elements are there, rock cycle is there, therefore. Next. So these have different strontium and neodymium isotope compositions. Next. You see, when we plot those rocks from Himalaya, high Himalayan crystalline plot here, 87 86 I see. Here, Islam neodymium. We have lesser Himalaya here, very high strontium 77. It is thought that metasomatic processes has enriched these lesser Himalayan rocks. High Himalayan crystalline rocks also very enriched. And next, you see lesser Himalaya. Then you have Thar sediments here. We have lesser Himalaya here, we have higher Himalaya here, we have Tibetan sedimentary, it is beyond Himalaya series, but these Thar desert sediments are plotting here in between. Why not it is plotting very near to high Himalayan or lesser Himalayan crystals? However, Ganga sediments are plotting here. The Thar sediments are plotting here. It is because Himalaya doesn't only contain higher lesser Himalaya, it also contains a craton like Tibetan sedimentary series, which is from that side, or suture zones. In the suture zone, which means basalts. Basalts have less rubidium, less strontium 87. So Tibetan sedimentary. So this Thar is not only mixture of higher and lesser Himalayan sediments. It also takes Tibetan sedimentary series in the Sanko suture zone material. See here. Then material have come from a river which was taking sediments from all these areas. Here you have for aerosol scientists, this one end member, Thar sediments, we have Ganga sediments. We can differentiate whether the sediments are coming from Ganga, Yamuna plain or desert. More work has been done in today's presentation. Next.
87, 86 initial storms.
इनिशियल तो पहले हुआ है, ये अभी वाला है, ये अभी वाला है. So accordingly, I have tried to show what is the isotopic distribution accordingly. We can divide this Indo-Gangetic plain, including Thar desert, into different geochemical provinces. So, radiogenic strontium, less radiogenic materials. Whole Ganga plain has 87, high 87. और दूसरा कारण है. See, Brahmaputra and alluvial, they are all bringing sediments from in the Sanko suture and all. They are less radiogenic in strontium and more radiogenic in material. This Indus, they are also bringing in the Sanko suture material more. They are also less radiogenic strontium, more radiogenic. But Ganga plain, more radiogenic strontium, less radiogenic. Different ones. Not only this. We have also characterized set rivers from this. They are also less radiogenic strontium. The only peculiar thing is about the Ganga here. They take more sediments from higher Himalayan basin. Therefore, this isotopic systematics can be very well used for the aerosol study to identify particulate matter whether they are originating from Ganga alluvium or Thar desert or which alluvium or which rock type. If they are coming from the Deccan basalts, they will have very much different, like previous one, like this. Sanko. They will have different strontium radioisotope.
I have recent data now. It says 0.734. Slightly right side transfer. So when is the next year?
735. So this isotopic systematics can be very much useful for the aerosol study as far as trajectories and their sources are concerned. So we can use major elements as I have shown you using CIA and ACNK diagram. We can use trace elements, rare earth elements, other trace elements also, how the patterns can be used, and third, the isotopic systematics. They all can be useful, and the chemistry is decided by geology. If we want to use fingerprinting, chemical fingerprinting, knowledge of geology is very much important. You have to see which rock type, the ages of the rocks, the strontium isotopes and uranium isotope compositions, not only the magmatic process, also the age of the rock, how much old it is, how much time it has taken to evolve, and then accordingly how much strontium 87 was found from rubidium 87. So geology decides the chemistry and everything as far as our environment is concerned. Thank you.
Thank you so much, sir. He is waiting and will take the question answers on T because our eminent speakers have very tight schedule. I would request Professor Dhar to please honor our eminent speaker, Professor Tripathi, with a memento and with a token of thanks. Thank you so much, sir, for a wonderful lecture. Very informative. And we are running out of schedule. We have to go out, grab, and come as soon as possible. As soon as possible. Please, ready. You can go out. We can take photograph and all. Please go out and come back. because these our speakers are leaving at 1 p.m. And Professor Sudesh is going to talk about ICP OES also, digestion methods also. So tea is not that important at present.